Good morning, good afternoon, everybody. I'm Mohamed, CEO and co-founder of Kolena. Today, we'll be chatting about how we can build a systematic model testing process in our organization that allows us to build reliable and trustworthy AI products that we can trust as builders and our customers can trust. Allow me to introduce myself first. I'm CEO and co-founder of Kolena. We're building AI testing and validation tools. I'm the author of Manning's textbook, Deep Learning for Vision Systems, and I previously led AI and ML organizations at companies like Amazon, Twilio, and Rakuten. We have an exciting agenda today. We'll first start with taking a look at the current ML evaluation approaches that we're using and implementing in our model development process. And we see how it might be falling short in building trust in the products that we're building. We're going to dive deeper into these aggregate metrics that we're using and how we see them as misleading and time-consuming to debug. We'll review the AI risk management framework that was published by NIST earlier this year. NIST is the National Institute of Standardization and Technology, belongs to the US Department of Commerce, and they are in charge of regulating or building the gold standards for AI quality in the US. Next, I will jump into best practices for model testing and validation to build trusted AI products. We'll go through unit testing for machine learning, how we can build the standardized quality process for our products, and how we can build the test and how we can build up an infrastructure to allow us to test end-to-end products, not just the model. And we're going to go through a quick recap. All right, so let's get started. How are we testing our models today? Let's take a look at the current approach. Today, we split our data sets into, we have some test data set, and then we run model inferences once we finish training. And then we produce some aggregate metric for the class for the whole data set. Like this model is 90% accurate or 90% on some metric. But it's not clear for us what is that 10% and which model is better, the 90% or the 88% or the 92%. All these details, we spend weeks as data scientists or ML engineers debugging our models, looking through tons of data sets just to understand how we can set expectations internally and externally with our product strengths and weaknesses. This current process now is an ad hoc process, time-consuming, and highly dependent on the scientist's intuition and their experience in this domain. The biggest problem of this is the current evaluation processes that we have for our ML products, they are completely decoupled from the business objectives that we're building the product for. So let's take a look at this aggregate metric again. Now, let's say you have a model and your version of that model is performing at 81% on some metric, precision recall, blue, rouge, however, like if it's a vision problem, structured data problem, LM problem, we have some metrics usually that we're measuring model performance with, and we say, okay, V1 of the model is 81% on some metric, and that improved in the next iteration into 85%. Now, at this point, there are three main questions that we always are trying to answer, but they are taking all of our time trying to debug the model. One is, which model should we deploy? Is the 85 better than the 81? Are we sure about that? Do we have an idea where it's failing and where it's succeeding? What has improved and what has regressed? We went from 81 to 85. Chances are, some scenarios have improved, some scenarios have regressed, some classes or subclasses or units that have improved and regressed, but it's not clear. We don't see that from that aggregate metric, and we're trying to look at the failures here, failures there, trying to assess manually with just our, trying to see patterns into where the failures are. So it's not clear where the model has improved and regressed for this metric. And the third thing is, are we confident that we thoroughly tested our models? That's the question we always get. Have we tested on this data that we got from that customer? Have we tested on the other data we got from other customers? We always get these questions as data scientists. We don't know what the test coverage looked like. Have we tested on that scenario that we just filled in? It's not clear for us. And because of that, us as the data scientists, we spend around 60 to 80% of our time trying to test and debug and validate these assumptions before we make a decision to deploy to production or improve the model. Okay, we need to improve in these areas. So we ran two case studies here that we're going to present to you guys. One on the computer vision side and the other one is in LLM side, just to capture most of the interesting use cases that people are asking about. The first one, we're looking at a case study that we're developing a computer vision model that detects persons. And we tested that on the COCO 2014 data set. When we test this, we see that, okay, we ran the model test on the mask RCNN. It's a kind of a multi-stage model detector. So we ran on the mask RCNN and the YOLO V4. We saw that on recall for the person detection, the person is the class, the model is performing the mask RCN 81%, and that for YOLO V4, it's 85%. Now, same question, same thing we've thought, which model is better? Which model to deploy for our person detection problem? So it's not clear at this point. And now we want to take a look at unit testing now for machine learning. It's a great time to introduce the concept. So unit test basically it's a group of data points that share the same characteristics that we want to test. So we start looking at, okay, let's look at our model results at the unit level. So we have built unit tests for this person problem, just as an example. One is looking at, okay, how is the model performing? Well, it sees the whole body in the image, right? So that could be straightforward. But we want to look at the model robustness, how robust it is to detect people or persons when it's seeing only the upper body of the person or lower body, or just parts of the body, head, arm, leg, and so on. Another test suite that we created is we want to see the model robustness in detecting people when the bounding box is small, and then medium and large and very big, which represents depth in many robotics problems. If we look at this here, we see that we are testing two models, and these are the metrics precision F1 recall that we're testing against, and we can customize that. You will see that in the next case study. But for now, looking at this, we see that the person detection at the aggregate metric, which is what we usually see in today's toolings, in today's in-house infrastructure, we see that, okay, the model performed 81% on recall, up to 85%. So it says that, okay, probably this YOLO V4 is best for our models. However, at the unit level, we start seeing that the model has regressed or performing poorly in some of the scenarios here. One is when it's only seeing the arm. So if the person's out of the frame and then just see the arm or the hand, the model has regressed from 74% on recall down to 67%, while it's improved in other areas. But this piece itself, this case or this unit or this scenario, it has heavily regressed. Now, the other regression we saw here that the model has regressed, or YOLO V4 is not as good or as robust in detecting objects or people in this case that are big or very big bounding boxes, or the size of the bounding box. Now, it's counterintuitive, right? You would assume that something is big, then it's so clear, the features are clear, especially in vision problems, but these nuances are very common in neural networks. It depends on what they have been trained on or what biases it has created when it's training its weights. So here, for this case, we have a lot of details, or we have high resolution understanding of the model performance to say, you know what, we don't care about the scenario, we're going to deploy the YOLO V4 anyways, or no, we care about these scenarios. I know exactly as a data scientist what I need to improve the model performance. I'm not shooting in the dark anymore. I'm not collecting all the data anymore or running a lot of experiments. I know that I need to improve in the arm scenarios. I will add more data in this scenario. And I need to improve in these larger kind of bounding boxes. Let's take a look at another example. In this case study, we're evaluating LM-based Q&A application. And we ran the test on the open source dataset called Conversational Question Answering Challenge. As you guys are familiar with OpenAI and other LLM company providers, but for OpenAI specifically, every company that's building LLM models or AI models, they produce some kind of performance card as they are releasing the models. This performance card, I linked it here for you. It's like 70-something pages, and it's showing that GPT-4 has improved against GPT 3.5 in the answering the right questions or truthful QA by around like 12%. So GPT-4 is around 60% correct, and then GPT 3.5 is around 50% correct. But that doesn't matter what the report cards say, because it's all about how the model is going to perform on my problems, on my data sets, on my scenarios. Now, we ran here the case study. We ran on this data set. We tested the GPT 3.5 Turbo and the latest GPT-4. We saw that on this data set, on the BERT recall score, the 3.5 performed 92%, and GPT-4 improved to 93.6%. That's on the aggregate level. But let's take a look at the unit level. So now we have created some unit tests. One suite here, or set of unit tests, that are looking at the source of the data. If you're looking at the RAG kind of problems, so the source here is Wikipedia, MC Test, CNN, Gutenberg, and we also broke our data down by the type of the question. Is it a who question? Is how, why, when, where, all these kind of questions to see how the model is performing for different types of questions. Now, in here, we're looking at the BERT recall score. So we see that, okay, for this problem here, GPT-4 have improved across all scenarios, except for two scenarios here, how and when. And the improvement here is not, or actually the regressions here are not so big. So 91% on the BERT recall to 90%, which is actually 90.9, so that's pretty close, 94.8 to 94.3. So I wouldn't call that too much regression. It could be the same, and then it has improved in other scenarios. That is the unit testing point. But now that I'm looking at this, we want to look at a different angle of looking at the results, which is applying some custom metrics. We'll talk more about custom metrics later in this webinar. But for now, since we're looking at the screen, I wanted to just share how we can make decisions on which models to deploy in a more holistic way. So if we apply a custom metric, we call it the correctness flag, and I'll expose the logic for how we can build this correctness flag for our LLM problems. But for now, we start seeing that when we're looking at a different metric, which is more related to the goal of that product, which is answering the correct answers to our questions, we saw that the model have regressed. GPT-4, which is double the cost if you're doing API calls, have regressed in all sections, not just the that didn't improve in any area, but it improved only on when the source is Wikipedia, which makes sense for us because we know that GPT-4 has been trained mostly on Wikipedia data. And it improved only on two scenarios of types of questions, is and was, which basically the same question or same type of question, just in the past tense or present tense. So that it's intuitive to see that the model has only improved in these types of questions. But here we're trying to show that in addition to looking at the unit test, it's much more direct and much more high fidelity, and looking into a custom metric or specific metric that represents the quality of our product. Now, these variations in the model performance at the scenario level, now this term has been coined by researchers as the hidden stratification phenomenon. Now, this phenomenon here in their paper, I cited the paper here for you to take a look at it, but the authors here ran a case study on an imaging problem in detecting cancers in X-ray imagery. And they saw that this aggregate metric that they have been tracking, we've been talking about that aggregate metric for a while, is skewed by a subset of the data that's not important, where the physicians have the chest drains in the images, whereas this green curve here is the important curve that they are trying to understand the model performance at. So the paper basically says that the hidden stratification phenomenon means that these aggregate metrics fail to capture the full picture, and the models exhibit highly variable performance across the subclasses or the different units or scenarios. And they stated at the end that these silent regressions between different scenarios happen every single time we update the model on new data, and we need to have systems in place and infrastructure in place to capture these silent regressions. So with that, to recap the problem part and jump into the solution, we have seen that the traditional testing and evaluation process leads to a uncertainty across all the parties that are involved in the development of ML products. Engineers are usually shooting in the dark. They don't know exactly what to improve, 81 to 85, so they are shooting in the dark in data collection, experimentation, labeling, and businesses are not able to explain the strengths and weaknesses of their products, and product managers are struggling to create clearly defined roadmap. We want to tell our customers, hey, this is how good our models are. These are the weaknesses. We're going to improve these weaknesses in the next quarter and the following quarter. This kind of conversation is really hard to have with AI product managers. And obviously, at the end, with all the unexpected model failures that are happening, customers are losing trust in AI. The National Security Commission of AI published a report earlier last year saying that the only way to minimize the performance, the problem or anticipated outcomes of AI models is that we need an entirely new type of test and validation framework. And they stated that we want it at the granular level or at the unit level. Earlier this year, NIST published an AI risk management framework. I dropped the playbook link here for you all to take a look at it. But for now, their intention is to equip organizations with a framework to increase the trust in their products or AI products that they're working on. They define trustworthiness as something that is reliable and explainable. We need to be able to explain to our customers and to our leadership where the strengths and weaknesses are. And the quality process has to be visible and transparent for everybody. They stated that they set the quality process as 3 main stages. One is mapping, which is identifying the model risks and edge cases. The way we call it is putting them in unit tests, and then manage them and track them across the different life cycle of the different stages of the life cycle. And then at the end, test and analyze, which is measure. We created a best practice for systematic and reliable model validation. That this process aligns with this process and works. We have seen it in action for all kinds of machine learning problems, computer vision, LLMs, generative models, structured data, and others. We published a white paper here on how to create a culture of quality in your organization. You can see it in kolena.io/blog. So the process is, we start with what NIST calls it mapping, with identifying risks. We call it curating high fidelity tests. We need a solution to be able to break our test data down into the right unit tests. So we're able to ask the model the right questions. How are you doing in this scenario? How are you doing in this scenario? And then we want to manage the distribution between our scenarios that we're tracking in our test data. Next, we need to standardize the quality rubric, standardize the test coverage, standardize success criteria or pass or fail criteria, and the metrics that we're using, like we saw the N number of, or the correctness flag for the LLM example. Third step is product level testing. We talk a lot about testing the model, but our models or our systems usually include pre-processing steps, post-processing steps, maybe on top of it there's logic, or there's a pipeline of models feeding each other. So we want to be able to test the end-to-end system, and we want to apply product level metrics, not just the traditional ML metrics like precision, recall, and others. Now we're going to go through each one of these phases to take a deeper look at them. Curating high fidelity test. Now, let's pay attention to our test data. We start seeing organizations, especially in the last 12, 18 months, teams and ML companies, AI companies started focusing more on their test data. Test data for us is like a test bank, right? Like this is your test bank, and then if the test bank is asking the wrong questions, you're not validating it right, or the test bank has wrong answers, which is your labels, right? Then you're not validating it right. So everything we know about the model behavior before we push it to production comes from the testing data sets. So we want to pay much more attention to that, and we can actually make the claim that properly managing our test data is much more important than our training data. We always think about the bias in the training data. We look at the distribution of training data, and that's not wrong. But a balanced training data doesn't guarantee a balanced behavior. That's number one. And number two, we're not expected to add every scenario that we are facing in production in the training data. That's counterintuitive to what machine learning is. Machine learning is supposed to learn from the data to generalize. Now, for us to test the generalization, we need to include every scenario in the test data. So that's, again, theoretically, the ideal case is chasing the long tail through the test data, not through the training data. So through the test data, it's used by ML engineers and scientists to test the model performance and guide the next steps of the process. Product managers use the test data to encode the product objectives. Business folks, external folks, customers, and others, they interface with the test data through us to understand the model performance. We communicate with them the behavior and the capabilities of the product. So we start seeing a paradigm shift to unit testing for machine learning. We've seen the way we live now, we split our data into train and test, and we have some arbitrarily unbalanced split for test data. We start seeing that moving into a more fine-grained and well-curated testing scenarios or unit tests. If you're doing an LLM problem, we saw the examples that we saw in the case study earlier. We're talking about how questions, when questions, and so on. That's all through the factualness suite, how correct or how factual the answers are. Well, there are different types of testings like jailbreak, like data leak, prompt injection, bias, adversarial attacks, and others. So there are tons of tests that we want to apply to verify that this LLM works well for us. Some applies for different businesses, some don't. So we need to start breaking the data down into unit tests to test different angles or different capabilities that we need to comply with, whether it's a regulation thing or it's a security thing, or whether it's actually the quality of the product or the capability of the product. Now, having broken this down, that allows us to look at the distribution of these scenarios in our test data. In this example here, we show you that, okay, we have a case that we have probably like 7 test cases here or unit tests. And we see that red curve represents the model performance, and the blue curve represents the distribution of the data in our test, or the scenario in our test. So if we're using aggregate metric, this model, while performing very poorly in this scenario D, this model will give us high score, because this scenario D is not well represented in our data anyways. But unit tests can show you exactly, yeah, you'll see this scenario at high score, but you will see as well that this scenario doesn't have enough data for you to have high fidelity test. So that was the first part of curating high fidelity test. Now, having done that, we need to standardize the quality rubric. If you remember, we said standardizing quality rubric, you need to standardize test coverage across the team, standardize the metrics, standardize pass or fail criteria. Let's take a look at them. So standardizing the test coverage. The way we look at our data now, or we test data, we just look at some buckets in our store of some data, whether it's vision data, CSVs, LMs, or language data, some docs that we have. It's not clear really what we're testing against. Now, instead of that, we want to start looking at our test data in test suites and test cases. You see here in this example, this is a text summarization problem. So like an example of text summarization model. And we're looking at, okay, this team has broken their data down into, so this is the news, like the actual example we're looking at here. They're summarizing, we're building a model that summarizes news articles from the CNN Daily Mail open source data set. So we see that, okay, the team here has broken their data down into test cases that represents different news categories like business, entertainment, politics, and others. And then they have another suite that's looking at the length of the article, which is something that affects the text summarization models. And jailbreak here, which is looking at the moderation or hate score. This is a suite that is, which specifically if you're testing on LMs, you want to know which is generative models. You want to know what type of hallucination it's doing. Jailbreak is an example of that. Having this standardized test cases visible for everybody in the team allows the team to build alignment and trust with internally and externally with their customers. This way to allow management, this is the test coverage, this is the regression suite. So every time you have people in the team, one scientist is debugging and added another 5 test cases, then another scientist comes after a few weeks or a few months, they are testing on the latest and greatest. Everything is managed on a platform or on a solution that is looking at test cases and test suites. So that's number one, standardizing the test coverage. Number two, standardizing success criteria. So here for this example, we've seen different teams applying different ways of pass or fail or success criteria. I'm going to show here 3 approaches, which are the most common ones. But again, happy to chat offline after this, see how you guys are doing this now and what kind of success criteria applies for your problem best. So in this example here, we're looking at one way to create success criteria, if you want to look at an aggregate metric that is more representative than the current aggregate metric that we look at, is applying some weights or applying some importance kind of score for each of these test cases or categories of test cases. And then at the end, you have a weighted sum of the model performance, but now it's more reflective than this kind of precision recall metrics that we look at. Another way we saw this is instead of applying weights, then what you can do is you configure your system, your testing system, that a model that does not regress in critical scenarios passes, right? A model that does not regress in these specific scenarios or is improving in these scenarios passing. So in here, you just say, okay, I want to be able to pass in this. I'm fine if there's no changes here. I'm fine for regressions here. But this is a way for you to break down, automate your problem after having broken it down into test cases. The third approach is applying some thresholds. The same way we apply thresholds today to our models, you can name these thresholds or configure these thresholds in your systems, which is basically, hey, if this top view kind of test case or unit test passes or is higher than the threshold, then it passes. Now, the third thing we want to standardize is the product metrics. Think about this, we're thinking about standardizing product quality, all of it. So the metric of pass or fail, something we need to standardize. And we looked at the earlier example, we looked at the correctness flag. So instead of looking at the traditional ML metrics, precision recall, red rouge, others, they are usually, or not usually, they are in many cases misleading, or a better or a more accurate approach to build product that you can trust is to build some logic or some metric specific to the goals of this product. Examples of this is we looked at the correctness flag. The correctness flag here takes into consideration the F1 score, Rouge score, and some threshold. This is just like a simple implementation for us to look at it in the slide. But we built a glossary or library of metrics. You can look at it in our documentation, docs.kolena.io, and we are going to open source this part. So please let us know if you are working on something different. Let's have this conversation and build a library for everybody in the industry. So correctness flag is one of those good examples for Q&A for LLMs. Collision risk for robotics. We'll talk about it in the next slides, but I'll skip it for now. Expected revenue if you're building recommender systems. Recommender systems, again, you're looking at precision, recall, AUC score, and others. But a better way to look at it is the expected revenue, because some model, while it's performing lower in score, but it's performing poorly on cheaper products, but it's better at more expensive products. So when you're building a recommender system, to be able to make an informed decision, you don't want to just look at the model performance from the machine learning perspective. You want to look at the model performance from the product perspective, from the business perspective. And in this expected revenue method, we took into consideration the product price, quantity remaining, click-through rate, and so on. So now we've talked about standardization. Last thing we would jump on is product level testing. Now, we talked about, today we've been testing our models, not the entire product. We just go ahead and test models and pick the best model and push it out to our system. But testing end-to-end system is a critical part of comprehensive validation for our products. A case study that we ran on the giant attention and autonomous driving data set, as we looked at, it's a video data set, and the goal of the problem we're solving for is detecting pedestrians and identifying whether they are crossing the street or not to avoid collision with the autonomous vehicle. So the system here is composed of two models in the pipeline, so a model feeding the other. And then the first model is an object detection model. We picked two open source models, sort and deep sort. And the second model is a classifier to detect that person that has been detected and classify them whether they are crossing the street or not. For this, we use the C3D and the static models. Now, you have two models in the class detector, two models in the classifier. This means that my pipeline have 4 different variations of 4 possibilities of what the pipeline would look like. If we test each model at a time, we see that the deep sort is better than the sort, and C3D is better than static for the classifier. Now, you probably see where I'm going with this. If you test the entire end-to-end, we saw that the sort and the C3D combination as a pipeline have higher performance than the 2 winning models, the deep sort and C3D. And the reason here is when we saw that the detector is detecting irrelevant people on the side that the classifier is failing at. So it doesn't tell us exactly how good the entire pipeline is going to perform. The other thing we want to test is use product level metrics. We talked about it in several areas now. I will give you another example of this. So instead of looking at precision recall for the same case study that we ran, if we care about recall more, which is false negatives, you want to make sure you're avoiding collision. Obviously, this is the most important part for this kind of application. We saw that system A missed 100 pedestrians. These are just example numbers. Missed 100 pedestrians, false negatives, and system B missed only 30. So at this point, I'm inclined to go with model B or system B because it missed less pedestrians, which means less people are at risk. But applying a custom metric that is testing the product level goal, which is collision risk, and a simple logic for a collision risk method can be, hey, if the detected pedestrian is a false negative and the distance is less than 10 meters. So you're talking about collision risk is not everybody is at collision risk, it's everybody that has been missed within the 10 meters depth, just as an example. Now that led to completely different kind of results that we're looking at when comparing the two systems together. We saw that system A, while it missed 100 pedestrians, only 5 of them were at the collision risk. Whereas system B is clearly lacking, or the performance is clearly poor for people at the danger zone or the closer to our pedestrians or to our vehicle than system B. So for this case, we're going to go ahead, with actual more insights into how the product is going to perform. We're going to go with the collision risk 5, which is system A. All right, so to recap what we discussed now, we we understand that building a systematic process or a culture of quality in our organization, it's not something that is an easy and quick thing. And it's something that comes iteratively by working in having a systematic way of validating our systems. It doesn't come through a heroic one-time effort from one of our engineers or a groundbreaking new architecture. To recap the three main areas that we talked about for high quality model testing process, we need to have unit testing for machine learning, standardize our quality rubric, the test coverage, the metrics, and the pass or fail, and we need to test at the product level testing. Now, we built Kolena to make this robust and systematic ML validation process easy and accessible for everybody in the organization. One slide just to take a quick look at what we offer at Kolena. We have three main components. First component is a data studio that helps you explore your data, analyze it, understand potential blind spots in your test. This is one of the biggest important things, to go through the unknowns, and create representative testing scenarios. In this screenshot, you're looking at images, but we support vision, NLP, and structured data and speech data. Second component is the standardization part. We need to be able to look at our test coverage. What are the scenarios that we're testing? What's the product quality criteria? What are the pass or fail criteria that we have? And then the third component is the high resolution results at the unit level. We're looking at the comparing the models at the unit level, not at the aggregate level that we talked about. And just here a slide to share that we talked about our first component here, the data studio. So we're looking at the vision slide, but we support speech problems, NLP or LLMs, like our language kind of problems, and structured data or tabular data. All right, so that comes to the end of our webinar today. Please connect with me on LinkedIn and Twitter if you have ideas to chat about. Would love to connect and learn more about what you guys are working on. I'll open it for questions. We have maybe 5-10 more minutes, so I'll open it to see if anybody has questions.
So just logistically, I hope everybody could see the Q&A widget at the bottom of your Zoom screen. And if you want, you can submit questions through that. Hopefully everyone can see it. But we're having some kind of trouble with the chat in this webinar. I'm not sure why.
Right, I see a question here. So somebody's asking, how do you establish test coverage? Trying to understand what you mean by the question, how we establish. So I'll try to give it a short answer if you have the chance to explain a little bit more. I'm reading. So the question is, how do you establish test coverage? Trying to answer this. So the test coverage is one thing, is actually creating this coverage and chasing these long tail of cases. And the other piece is managing it. So I'm assuming you're looking at how do we know what the test coverage look like? And this comes really in the infrastructure that we're building. So in Kolena, in the studio, we show you, we analyze millions of test runs that are running on Kolena, and then based on the problem, we tell you, hey, this is a bounding box problem. Here are others recommended testing cases or dimensions that you need to look at, like look at the size of the bounding box, look at the number of bounding boxes, look at dark, bright, or blur, and others. So we at Kolena, so it depends on the infrastructure that you have, but the solution we built here at Kolena, we recommend potential blind spots and other edge cases that you have. Our customers start usually with 5 or 10 test cases or unit tests that they think about. And we like to think about Kolena as your AI testing expert. You guys are experts in your domain. Kolena is expert in testing. And then our customers start from 10 test cases. Within a few weeks, they jump to 50 to 100 to a couple hundreds within a couple months. So we solve this problem on the solution side, just to answer the question. But happy to chat deeper about this if you meant something else for the question. Cool. All right, so we have Karen here asking, what does the data annotation process look like? Is there a need to scale beyond internal ML engineers and product managers? I think this would be needed to classify test cases. All right, that's a good one. We built here a studio to, oh wait, let me just show something. So if you're thinking annotation here as in how do we need annotation to extract scenarios, like you want day, night, rain, snow. We don't want you to do that. So that's why we built the studio. We allow you to search and slice your data based on scenarios, similar data points, edge cases, clustering, view. So we give you the tools here. We're not expecting, as Kolena, we're not expecting you to have triaged your data or you have labeled your data with these scenarios. What you just need is your ground truth, which is a prereq for your problem anyways, if it's a supervised problem. If it's not a supervised problem, then you don't need ground truth at all. So Karen, just to answer your question, you don't need to scale your annotation process at all. If anything, we built Kolena to avoid that, right? Because the only way today to do it is you have to label your entire data with the scenario that you're looking for to be able to extract it. And then few months come back, and then you see, okay, I want to extract another scenario, and then you have to relabel the entire data. So we built toolings for this. You're not expected to scale your data annotation process. If anything, we've seen our customers saving somewhere between 20 to 40% of their data labeling of effort, time, and cost. Another question: are you able to test for harmful mode? Are you able to test for harmful mode outputs across? Yes, absolutely. That's the point of breaking things down into testing scenarios. When you are looking at one bulk of data, then you're just forced to look at the regular metrics of model performance. But an example of privacy, we have customers in the healthcare side. They created a metrics that are looking at PII data that's leaked. That's not machine learning problem. It's just a software problem now, and then you're able to just identify any PII data. So yes, for sure, to answer this question, that's the point of breaking things down into test cases so you can have a privacy suite and a robustness suite and safety suite and so on. Skip is asking, how is Kolena different than weights and biases? Weights and biases is a neighbor in the stack. They come in before Kolena, and the training, it's an experimentation tracking product. Most of our customers have something similar, either weights and biases or MLflow or Comet ML. These tools are focusing on tracking your experimentations for reproducibility, and they deal with the model training and validation data sets. And they track things at the aggregate level too. Kolena is focused on robust testing. So robust testing involves data management, like you're seeing on the screen, and breaking them down into edge cases, understanding the blind spots in my data. So there's a lot of data here, curation that's involved, and then tracking these test cases. So that's more of a project management or a framework that Kolena provides, and then creating results at the unit level. So every tool provides some reports. Kolena reports provide the examples like you saw earlier in the case studies at the unit level. Awesome. I don't see any more questions. Thank you, everyone, for joining. This is great. We will be sending an email with the recording for everybody, and I would love to connect with everybody here. Thank you. Have a great rest of your week.